Hello everyone, I'm Nikhil Malik, working as a principal engineer in Netlog, South Korea. The topic of this talk is end-to-end SCTP multi-homing with eBPF. In this talk, we will briefly touch upon basics about SCTP multi-homing and related problems with load balancers, why we chose eBPF to implement SCTP multi-homing and how we leveraged it. Next, what all challenges we faced with eBPF, and at last, some performance analysis. SCTP protocol with multi-homing enhances the robustness, reliability, and efficiency of network communications across various applications, making it a valuable protocol choice in modern networking areas. As the networking world has evolved to cloud-native deployments and microservices in the cloud platforms such as Kubernetes, introduction of stateful load balancer for hosting services has introduced many challenges, especially for multi-homing features. The problem persists with monolithic systems with standard stateful load balancers as well. When SCTP connection establishes, most of the stateful load balancers track the connection and maintain only the primary address information about SCTP endpoints, unable to leverage core offerings of SCTP multi-homing. To support multi-homing, it would be required for a load balancer to host SCTP service with primary and secondary IP address and share them with both the endpoints during SCTP connection establishment. Map load balancer IP addresses with endpoints, primary and secondary IP addresses, manage multiple network paths, calculate checksum after NAT, and most importantly, load balancer should not introduce any significant performance overhead. eBPF technology is a very well-known performance technology which can provide tools and methods for every requirement stated previously. Each SCTP endpoint share its secondary IP information during connection establishment in init and initat packets. Once the primary and secondary IP information has been received from both the SCTP endpoints, then it would be required to map them with the load balancer IP address and stitch a bidirectional path for the traffic. LogCLB uses eBPF maps a key value store to store all the information which can either be used by eBPF program or its user space application path to take the necessary action on the incoming packet. It takes a multi-transactional update to the eBPF map table to add all the entries related to a particular connection. Although eBPF is the state-of-the-art technology with many benefits, but it has its own challenges such as limited instruction set size, deleting map entry in the loop, limited helper functions for SCTP in the kernel, and it becomes increasingly difficult to calculate CRC32 checksum for bit size packets within the limited resources. eBPF allows section where you can have a reentrant code for checksum calculations and use tail calls to jump back and forth between them and finish the task, but tail calls are costly. So by reducing the number of tail calls and batching packet reads in the chunks in LogCLB, we were able to improve the performance from 242 Mbps to 1.4 Gbps. For further optimizations, we are targeting to replace tail calls with BPF loops. Last year, we presented state synchronization of eBPF maps where we discussed how state information in eBPF maps can be synchronized with cluster-wide peer entities to provide hitless failover. This year, we extended that infrastructure to support SCTP multi-homing features as well. All the network paths in the SCTP association will now be synced with peers via gRPC. In case the active LogCLB instance goes down, then the connection will not be disrupted as all the eBPF map entries are synced with the peer instance. This is the topology we used for our analysis. We evaluated our solution with Seagull as client and server. Seagull is a multi-protocol traffic generator which is used as a standard to test telco traffic. The aim of these tests was to observe any performance overhead by introducing a load balancer. You can find the description and link to this demo in the comment section. Our first test was standard calls per second where it was set to 5000 CPS. We observed that introducing LogCLB as load balancer did not add any performance overhead. Our next test was to observe and compare the recovery time and rate after the primary network path is down. We observed that path failover time was not impacted by introducing LogCLB. Though the recovery rate of failed calls was better with LogCLB, this was because of the LogCLB's eBPF data path capability to process the SCTP packet faster, which helped in clearing the backlog. Lastly, we thank you for your time. Please do visit our GitHub and website to check out more. Thank you.